Hello friends, we will be starting with simple stress and strain. First, coming to stress. Stress is an internal resistance offered by a body against the deformation or external force. I think all of you know what is stress. Okay, so it is represented in Newton per mm square or Newton per meter square, what we call it as Pascal, and it's a second order tensor. What is a tensor, that we'll deal later. Whereas pressure is an external force distributed over an area or unit area. Usually this is the main difference. Okay. Stress, for example, if you have a small body and you are going to apply a force on that particular body, inside the body there develops a small resistance against the applied force. This we call it as stress. Whereas pressure is on the same body. If a small forces are distributed over the entire surface, this we call it as pressure. So this is the main difference. Coming to the different types of stresses, normally stress, we say stress, then it is force divided by area. Here the main thing you should note is about the area. So if you consider the actual area for the calculation, then it becomes the true stress or actual stress. Okay, for example, if you have a rod, okay, of diameter say around 20 mm, you are going to apply a force, say P. Okay, when you apply this, after the application the bar is going to increase its length in the length direction. For example, if this length is L, okay, the length has been increased, okay, from L to L plus delta L. In the meantime, the diameter has been reduced. For example, this may be 20 mm and this may be 10 mm. This may be example. So here stress F or P, whatever we call, okay, is nothing but load by area. Here area, if you consider area is equal to pi by 4 d square, where d is nothing but 20 mm, then this is the initial area what you are taking, or initial diameter what you are considering. Hence this stress corresponding to this particular diameter, we call it as engineering stress. At the same time, if you calculate the stress based on the diameter where d is nothing but 10 mm, then this is the original diameter at the time of application of load. Hence, if you consider this diameter for the calculation of stress, then the stress what we get is the actual stress. So it can be mainly divided into two types. One is normal stress, second one is true stress. Normal stress is directly what we do is load by area, whereas true stress is load divided by actual area. So it can also be written in the form of a small formula or relationship, that actual stress is equal to normal stress into 1 plus epsilon naught, where epsilon naught is the engineering strain. Okay. If the load applied is tension, okay, then the relationship is sigma A is equal to sigma naught plus sigma naught into 1 plus epsilon, whereas if the applied load is compressive load, then actual stress is nominal stress into 1 minus epsilon naught, where epsilon naught is engineering strain. This is one of the formula. Okay, you should remember this formula. Similarly, strain, here strain, I think all of you know what is a strain. Strain can be change in some parameter, for example change in length divided by its original length. This we call it as a strain. Okay, so again it can be divided into two types. One is engineering strain, One is engineering strain, which is the normal case delta L by L naught, where L naught is the initial length. Usually we consider this for all the practical purposes. Okay. The second strain is a true strain. That is, for example, you have a same example I can explain. You have a bar of diameter 20 mm of length L. It is subjected to force P. Okay. After application of the length has been increased. Now strain, if you calculate, the strain is equal to change in length, that is delta L, divided by, if you consider this particular length for the calculation of strain, okay, then it is called as normal case. If you consider this length for the calculation, that is L plus delta L for the calculation of strain, then it is called as actual strain or true strain. This is the main difference. So here we have the second case is the actual strain, that is nothing but epsilon A delta L divided by actual length, where actual length is nothing but initial length plus change in length. If tension, it may be plus. If compression, the length will be reduced, so it will be minus delta L. You should note one more thing. Since a change in length and a change in area is difficult to calculate each and every time, for all the practical reasons, epsilon is considered. That is initial strain or change in length divided by initial length is considered for all the engineering calculations. The next part is stress strain curve for the tension test for mild steel. Usually we call it as ideal stress strain curve. This is the ideal stress strain curve, where strain is plotted in x direction and stress is plotted in y direction. You can see many figures. This is O. Okay. Here you can see initially there is a straight line and there is a point A, B, C, C dash, D, D dash, E, E dash, F, F dash. A we call it as proportionality limit, already written. Okay. Up to this point, stress is directly proportional to strain. You can see a straight variation. So up to this point, Hooke's law is valid. Okay. From A to B, it's a small curve, hence it's not linear. From A to B, it's a small curve, and B is the elastic limit. It is a limit. If you remove load from this point, okay, the material or the specimen will regain its original shape and size. And C and C dash, these two are the, one is upper yield point, second one is lower yield point. Okay. Yield means the material will start increasing its length without any further increase in the particular load. Okay. So there is a small gap between C to C dash. This point you should note, this is mainly because of the slipping of carbon molecules, or you can see the points what you have to note down. The decline in the stress value from C to C dash is due to slipping of carbon atoms in the molecular structure of steel. This once it has been asked in the competitive exams, hence that point has been noted. Okay, and coming back to our stress strain graph, you can see there is a this range C dash to D, we call it as plastic range, and D to E we call it as strain hardening, and E to F we call it as strain softening region. This is the normal case, that is stress is calculated based on initial area. If stress is calculated with respect to actual area, the stress diagram will go something like this, and fracture point will be above the ultimate point. So many points you should note about this stress strain diagram. First, plastic strain is 10 to 15 times that of elastic strain. That means from this point up to this point we call it as elastic strain. This length is nearly, actually in the figure it's shown larger. In actual practice, if you see, this length will be nearly if you multiply 15 times, you will get this length. That means this length is 15 times more than this particular length. Similarly, this length is 20 to 30 times more than this particular length. That point you should note. Okay, the second point already I have told. The third point is, in case of mild steel, A, B, C are very close. However, C dash is greater than B and A. Since A and B are close, mild steel is called linear elastic material. As per our Hooke's law, stress is directly proportional to strain up to proportionality limit, but A and B are very close. You can also consider this as up to elastic limit. And one more thing you should note, yield stress value and this proportionality limit are almost same value, hence this value is considered for all the practical purposes. Coming to the next point, this is the stress strain curve for other grades of steel. Okay, you can see this is other forms of steel. One is, this is the stress strain diagram for mild steel, and this is the stress strain diagram for torch steel. Torch steel is nothing but cold twisted steel. Okay, this is the same thing, stress strain diagram for high tensile steel. Okay, in all the cases you can see the initial lines are same. That means stress to strain relationship is same. That means Young's modulus remains same for all the types of steel. One more point you should note down, if you increase the carbon content of the steel, okay, you can note mild steel has less carbon content and it has got larger value of strain. As we increase the carbon content, the strain value goes on decreasing, whereas the ultimate value goes on increasing. Similarly, this STS got more percentage of carbon, hence the strain value has decreased more and its ultimate value has increased from these two parameters. So this point you should note down. If we increase the carbon content in steel, fracture strain reduces, ultimate stress increases. Coming to the next concept, that is stress strain curve for mild steel in compression. Okay, you can see the stress strain diagram of mild steel. Okay, here again the same thing, graph is plotted against strain and stress. Okay, and it comes something like this. This is the nominal case where the area is considered is the initial area. If you consider the actual area, the stress will be less in case of compression. And this point you should note, the yield stress value for mild steel in tension it is 250 Newton per mm square, and in compression it is 263 Newton per mm square or MPa. Okay. Similarly, this is the stress strain graph for other metals. Okay, there is a sometimes in the match the following you will get a problem or the this type of combinations. Here the first one is rubber. I didn't. This is elastic rubber we call. Okay, this is concrete, stress strain diagram for concrete, above which you will get the wood, and this is cast iron, and this is mild steel. Okay, here elastic rubber represents non-linear elastic behavior. That means from this point up to this point it's a non-linear behavior, and you can see A is the proportionality limit as per our mild steel is concerned. Okay. From O, you can consider this as O. From O up to B, it is elastic limit. From B up to F, it is a small gap. Okay, here this is the fracture point. So you can see just after the elastic limit, for a small distance, this rubber material is going to crack. So since it doesn't have a larger value of elasticity, this is considered as brittle material. So rubber is a brittle material. This is what you have to mainly note down here. Okay, you can see in the steel, if I, this is the proportionality limit A, okay, B comes here and C comes here and CD, B is here and the fracture point of mild steel is here. From B up to mild steel there is a large gap, nearly 30 times the initial stress gap will be there. Okay, so this is more elastic compared to your rubber. Since after elastic limit there is a small distance, this rubber is going to break, whereas in case of mild steel, from the elastic limit up to the fracture you will get nearly 30 to 40 times the increase in length, or 40% of increase in length you will get. Hence you can say steel is more elastic than rubber. This is the main point you should note down. Next, coming to next point. Generally, brittle materials are strong in compression but weak in tension. This is the point you should note, since they will ask these questions in the competitive exams. Okay, in match the following or two words or something like that. So generally brittle materials or brittle metals are strong in compression but weak in tension. However, most of the ductile metals are nearly equal strong in tension and compression. Brittle metals means, for example, you have glass, cast iron, all these are brittle metals, whereas ductile metals are mild steel, gold, silver, etc. Okay. The yield point of most of the metals decreases with increase in temperature. These are some of the points you should note. Okay. Coming to the next part, you have ductility and brittleness. So coming to ductility, those metals which have more than 5% of post-elastic strain, that is permanent strain, before fracture are called as ductile metals. As I said in the case of rubber, you can see this we call it as a post-elastic strain. Okay, here what I mentioned, post-elastic strain, this is nothing but, or the permanent strain is nothing but after elastic point, this distance we call it as post-elastic strain. If some material has more than 5% of post-elastic strain, that materials we call it as ductile materials. Whereas if you don't have more than 5% of strain, then it is called as brittle material. And that is the reason why rubber is called as brittle material and mild steel we call it as ductile material. Here for the ductile material we have mild steel, aluminium, copper, gold, etc. Due to this property, a piece of metal can be converted into wire or thin sections. Okay, this is also you should note. The second brittleness is nothing but those metals which have small, less than 5% of post-elastic strain, that we call it as brittle materials or metals. For example, cast iron, brass, bronze, glass, concrete, wood, rubber, etc. Coming to the next property, that is malleability. It is a property of metal by virtue of which metal can be converted into thin sheets. Okay, I think there is no complication in that. Coming to the next part, we have hardness. It is the resistance offered by a metal against the scratch or abrasion. Okay, that we call it as hardness. This is only the property. Okay. Coming to the next part, this is the most interesting topic, that is strain energy. Okay, how to calculate strain energy? Already it is the formula. It is a half into stress into strain into volume. Okay, coming to the topic strain energy, I can explain it in a different way. Just understand it. You have a small bar. Okay, I will apply a force P for this particular bar. So what happens is when I apply a force P, the bar will increase its length. Okay, this much length has been increased, that we call it as delta L. Okay, that is by the application of force P. And note that the load applied is within the elastic limit. So if I remove this load from the present state, this bar will regain its original shape and size. It will regain its back to the same shape and size. So from this position, it has gone back to this position. So some work has been done in order to convert this length into this length. So there must be some force inside this metal which converts the total this length into this length. That energy we call it as strain energy. When we apply a force on a metal, this metal, inside this metal, that develops a energy, that energy we call it as strain energy, using which it regains its original shape and size. Okay. If this the applied load goes beyond the elastic limit, then this length will not regain its original shape and size, because the strain energy stored inside will be lost in the form of heat. So this we call it as strain energy. And how to calculate strain energy already I have given you, that is it is half into stress into strain into volume. Okay, that is that we can get it from the load diagram or a stress strain diagram. You can plot a stress strain diagram initially up to the elastic limit. If you plot, it will be something like this. This is stress, this is strain, we call E. Okay, this area we call it as strain energy. So calculation of this area is half into base is epsilon and height is stress. This is of a of some metal. Okay, if you want to calculate for the full length, then you need to multiply with the volume, so that you will get the strain energy in the total volume. Okay, so here I have given the description. When a work is done by a load in straining the body, and energy is stored inside the strained material, this energy we call it as strain energy. Okay, coming to resilience, the strain energy per unit volume we call it as resilience. Okay, that means if you have in unit volume, one unit volume, what is the strain energy can be stored, that we call it as resilience. Okay, it is also known as strain energy density. Usually density weight by volume, in the same way it is strain energy by volume, that we call it as resilience. Okay, usually it is it can be represented something like this. Resilience is written in small letter u, which is total strain energy divided by volume. So it is equal to, strain energy is nothing but half into stress into strain into volume. So that volume will get cancelled and you will remain with half into stress into strain. So it can also be written as half into F into E. Okay, and E can also be written as F by E. So resilience formula comes to be U is equal to F square divided by 2E. Okay. In the above topic, if this particular stress is equal to the proof stress at the elastic limit, corresponding resilience V is called as proof resilience. Okay, expressed in joules per meter cube. And proof resilience is also known as modulus of resilience. Hence, the meaning is very simple. If this limit, this is the point, if this point, if you do it in a case of a cast iron or something, for example, the stress strain diagram for cast iron will be something like this. Initially it will be straight, beyond which it has For this, you need to calculate the yield stress by considering the proof strain, that is 0.2% of strain you should consider, and this value you should consider. This we call it a proof stress. If the applied load comes and reaches here, this area is nothing but proof resilience. The strain energy corresponding to this particular stress system, that we call it as proof resilience. Okay, coming to the next topic, it is elasticity. It is a property of a metal due to which removal of load, the original dimensions of the specimen will be recovered within elastic limit. Curve, this elastic limit curve may be linear or non-linear. For example, we have for mild steel. For the mild steel stress strain graph, if you plot, it will be a linear. The loading curve and the unloading curve will be linear. Whereas for the in case of rubber, this is the stress strain graph for rubber. This is the loading curve, whereas this is the unloading curve. So this is not a linear, this is non-linear behavior. Okay. But this limit is also called as elastic limit, because up to this point, if you remove any load, it will regain its original shape and size. Only thing is the loading curve and unloading curves are different. Okay. So most of the metals represents the same loading and unloading curve within elastic range. However, rubber is an exception which represent hysteresis loop. This is one more thing you should note down. This is hysteresis loop. The loading curve and unloading curves are different. For the case of rubber, this type of stress and behavior, we call it as hysteresis loop. One more parameter comes, that is when a metal is loaded and unloaded, a small portion of energy is stored inside the material. And if this loading and unloading process continues, this energy gets accumulated, and when this energy becomes equal to strain energy due to fracture, okay, any further addition of energy will cause the failure of the metal. This is one more point you should note down. Okay. Coming to the next topic, you have different types of metal behavior. First metal behavior is linear elastic. That means stress strain, in the stress strain diagram, if the line is linearly varying up to elastic limit, that is point B, usually we represent, and that type of behavior we call it as linear elastic behavior. Whereas you have any curve or any other shape, that we call it as non-linear behavior. Okay. And sometimes in some metals or some materials, you have a straight linear variation up to one point, then there is a clear plastic variation. So that type of variation we call it as elastoplastic variation or viscoelastic. And if you have if you have a line something like this, it is at up to certain stress value, there will not be any deflection or deformation. When it reaches a particular values of stress, everything breaks down and there will be a lots of variation or loss of deformation in one exact point. That we call it as perfectly plastic. Similarly, this is the ideally rigid, there will not be any deformation. That type of material we call it as ideal rigid, and I think that type of material is currently not available. It is only the imaginary part. Similarly, we have ideal fluid. Okay, again this is also an ideal case as the name indicates, because this type of material is not available. Similarly, if we have a linear variation for the initial time, then it changes its slope, okay, by to any other side. That type we call it as strain hardening. After some point, again it gains some strength or loses some strength. So This type of variation we call it as elastoplastic with strain hardening. I think this portion is not visible. I think now we can see this. This type of variation we call it as elastoplastic with strain hardening.